Hello everyone and welcome to McLean 360. So in this video I want to solve a problem with you to illustrate the concept of oblique stresses or stresses on oblique axis. Alright, so let's read the problem together and solve it. So we have two wooden members of uniform cross section, and are joined by the simple glued scarf splice shown. So knowing that P is 11 kilonewtons, we should determine the normal and the shearing stresses in the glued splice. All right, there is a follow-up question where we are given, the maximum allowable shearing stress, and then we have been asked to find the load P and then the tensile stress. So let's start from the first part. Now think about this surface. So this is what we want to do. We want to try and sketch that surface here. So you have your wood here, okay, and this one, so this is the normal wood here, but due to the cut you would see something like this due to the cut. All right, now think about it this way. This is your axial axis which is passing through the body, and there is this sort of normal which is perpendicular to this whole surface. All right, so there is this normal which is perpendicular to this whole surface, but then this cut is actually 45 here. So we expect that this angle, in other words, in fact, this angle here must be 45. All right, why are we saying this? So we are trying to say that the angle of inclination is 45. Whenever you draw something like this, there is going to be the shear force, and then also there is going to be the normal force. So if I consider the normal force is going to be, okay, so let me clean the normal axis. But then whenever you introduce a cut, there is going to be this normal force which is sort of perpendicular to the surface, okay? So we call it F. That is the normal force perpendicular to this surface. Please, it is perpendicular to this surface, okay? But the normal axis is like perpendicular to the whole of this structure. The F is when I take that cut. All right, and then finally so P is this axis. However, our cut is along this line, okay? Therefore the axis, okay, so we have our shear force in this direction, so we call it V. Now interestingly, the angle between the shear force which is along the direction of the cut and then the normal force F will always be 90. All right, so think about it this way. This is our P, and this P is the axis along which you have this. That is the P, the axis which is passing through the body, okay? So the angle between P and then the shear force is the same as the angle of the cut. Therefore we expect that this angle here must be what? 45. However, we know that there is this normal, so there is this normal to the plane. So the normal to the plane will be perpendicular to P. Therefore this angle here must be 45. All right, now it is interesting to know that the angle between the shear force V, which is in the line of the cut angle, and then the normal force to the plane, that angle should always be 90. So we are saying that this angle here should always be 90. So if this is 45, then this must also be 45 degrees. Is that right? So we are saying that this is also 45. Okay. Think about it again, that if this is 45, then clearly we can see that, okay, so if this angle here is 45, so now we know that from here to here is 45, here is 45, here is also 45. So what must be here? So we can look at the angle on a straight line, then we will realize that, in fact, 45 plus 45 plus 45 will give us 135. And then 180 minus 135 is 45. So interestingly, this angle here will also be 45. Wow. So after getting this, we can actually project this. So we can project the vein here. Okay. So we can project vein here. Okay. All right. So now if we do this, don't forget that the angle between F and V is 90. Okay. All right. So simply put, if we look at this triangle, what do we see? All right. So cosine 45 will be adjacent. So cos 45 is equal to adjacent. And in this case, our adjacent will be this component, this side, which is F, divided by the hypotenuse, which is P. So this side is P. You know, the 90 degree here is facing P. So it's going to be F over P. In other words, F is actually P cos 45. All right. Again, if we do sine, so sine 45 is going to be opposite, which is what? V, divided by the hypotenuse, which is what? P. So we have so we are going to have V as P sine 45. Okay. So if we want the normal stress will be the normal force on the area divided by A theta. Okay. Now, if we want A theta, okay. So let's do this again. All right. So to get the original, to get the A theta, now think about it this way. You can see that the original cross-sectional area is this portion, okay? And then the inclined surface area is this part. Is that right? Now, this is how you can look at it. So I have an angle of inclination here, all right? Therefore, I can say that this inclination is what? A theta. And then this side. Okay, so think about it using this one. A original. So A original. And this side is what? This side is A theta, the inclined side. So clearly cos 45 will be A naught over A theta. In other words, so all what we are trying to say is that A theta will be A naught over cos 45. So quickly, let's try to arrange all of this together. So this is what we are trying to say. For the normal stress, we will get F over A theta, and F is P cosine 45. And then I'll divide this by A theta, which is A naught divided by cosine 45. So I'll get P over A naught cosine squared 45. All right. And then my shear stress tau is going to be the shear force over the A theta, which is actually P sine 45 divided by A naught divided by cosine 45. So for the shear stress, I am getting P divided by A naught cosine 45 sine 45. Okay, so now from here we can clearly see that our normal stress will be P. Okay, so by the way, P is 11 kilonewton. Okay, so 11 multiplied by 10 to the power 3 divided by A naught. What is A naught? So A naught is 75 by 150. Okay, so 75 by 150, and then cosine squared 45. So let's pick our calculators and calculate the normal stress. So it will be 11 times 10 to the power 3 divided by 75 times 150. Then I'll multiply this by cosine 45 squared. And what is that? All right. So we can see that our normal stress is going to be 0.48. Okay, let's say 0.5 megapascal. Okay, and then our shear stress will be 11. Okay, let me do it this way. So our shear stress will be 11 times 10 to the power 3 divided by 75 times 150 cosine 45 sine 45, so that our shear stress will be okay. So our shear stress is also interestingly the same. Okay, so 0.5 megapascal. All right, so that is it for you. Now the second part of the question, this time around, knowing that the maximum allowable shearing stress is 620, we should determine the largest load P that can be safely applied. Okay, so knowing that the maximum allowable shearing stress, so that is this formula. Shearing stress is P over A naught cosine theta sine theta. Okay, knowing that the maximum allowable shearing stress is 620 kilopascal. So 620 kilopascal, which is the same as 0.62 megapascal, we should find the load P. All right. All right. So it's just a matter of change of subject. So let's make P the subject. P is going to be tau multiplied by A naught, all divided by cos theta sine theta. So it's going to be 0.62 multiplied by A naught, which is 75 multiplied by 150, all divided by cos 45 sine 45. So P is going to be 0.62 multiplied by 75 multiplied by 150 divided by cos 45 multiplied by sine 45. So we get 13,950 newtons. 13,950 newton, which is 13.95 kilonewton. So that is P. The next part of problem 2 is saying that the corresponding tensile stress in the splice. So now we know P. So put it into the stress equation. That's all what he's saying. So the stress is going to be, so P over A naught cosine squared 45. But then this time round, we are going to use the P that we have gotten. So it's going to be 13.95 times 10 to the power 3 divided by A naught, which is 150 by 75. And then we will multiply this by cos squared 45. Now, if we do this, then the normal stress will be 13.95 times 10 to the power 3 divided by 150 multiplied by 75, and then multiplied by cosine squared of 45. Okay. So, wow. So again, we are going to get 0.62 megapascals. That's interesting. All right, so this problem has been solved. In most of the textbooks, they don't try to sketch this diagram, but it's very much important to know how the formulas came about. Thank you very much for watching.